Okay, last lecture we were in chapter 11 of the curriculum. We talked about IPv4 address structures, looked at a different way. We can talk about the types of IPv4. We talked about segmenting a network, and we started to talk about subnetting a network. So we're going through some examples of that. Where we need to pick up is in 11.6, and 11.6 is talking about subnetting given /16 or a /8 prefix. So here in 11.6.1 it says creating subnets with a /16 prefix. I really think the word from might be better because that implies we're given a /16, and then from that we're going to create a number of smaller networks. So I think that might have been, I don't know if this is a mistake or just they thought that was fine. So basically, when we subnet a network, we talked about this last lecture, we're going to do what's referred to as borrowing bits. So we're going to take bits out of the host portion of the address, declare that they're new subnet bits. So what they're doing here is they're showing you all the possible things that we can go through and do. So basically, if we go from a /16 to a /17, we're borrowing one bit. And if that becomes the new subnets, that bit can either be 0 or it can be 1. So we actually have two subnets, and with the remaining bits we can have 32,766 usable hosts. So because again we have the network address and the broadcast address. So here they're showing that by bolding the new network bit, the bit we borrowed. One formula that you need to know is 2 to the n, where n is the number of bits you borrowed, is the number of new subnets you can have. So here we borrowed 1 bit, 2 to the 1 is 2. If we move down here and borrow 2 bits, 2 to the 2, or 2 squared, is 4. So we have 2 bits here. They can have possible combinations 0, 0, 0, 1, 1, 0, 1, 1. So those are the 4 new subnets. And each of those new subnets can have 16,382 hosts in it. If we jump down here to the bottom where we're doing a /29, we're actually borrowing 13 bits. 2 to the 13 is 8,192. That leaves 3 host bits. The other formula I think we talked about last time is the number of usable host addresses is 2 to the n minus 2, where n is the number of host bits. So in this case, we have 3 host bits. 2 to the third is 8 minus 2 for the network address, and the broadcast address leaves us with 6 usable hosts. And then finally, /30, which is the most bits we can borrow. The reason being we have 2 host bits. 2 to the 2 is 4 minus 2 is 2 usable hosts. If we went any further, we would end up with a subnet or subnets that could have no usable host addresses. We would simply have the 0 and 1, which would be the network number and the broadcast number. So this is them going through showing you that for all the number of bits we can borrow from a /16. So now there's a couple of ways to do subnetting, and what we're going to do is we're going to start out with subnets that are equal in size. So we'll either be subnetting for the number of subnets we want, or we may be subnetting for the number of hosts that we need on a network. So here we start with a /16, and important formula when we're trying to determine how many bits to borrow is 2 to the n needs to be greater than or equal to the number of subnets. So for the smallest value of n that satisfies that equation. So what happens is they've kind of gone through and shown you this, but we want 100 subnets. So n equals 7 is 128. So for n equals 7, that's the smallest value that will allow us to have 100 subnets. If we go down to 6, we have 64, which does not meet that. And again, we want just the bare minimum number of subnets so that we have the largest subnets possible. So what that means, since n is 7, is that means we're going to need to borrow 7 of the host bits. And when we borrow 7 bits, we add those bits to the network portion of the address. So we started with a /16. We add 7 to that because we're borrowing 7 bits. So we end up with a /23 subnet mask, which is what they are showing us here. So we borrow the 7 bits, and then we have the remaining 9 bits left for the host portion. Now then, we refer to these as subnet 0, subnet 1, etc. And basically what they're showing you down here is, since we borrowed 7 bits, they're showing the subnet mask, which is a /23, like we saw up here. And then what we're going to do is, in these 7 bits here, we're basically going to count in binary. So this is 0, this is 1, this is 2, we would have 3, we would go to 4, all the way up to actually having all those host bits set to 1. So what they're showing over here in the purple is the network number for each of these new subnets. And again, the way we get the network number is by setting all the host bits to 0. So, the first subnet would be 0.0, the next would be 2.0, the next would be 4.0, all the way down to 254.0 for the last subnet. So what they're doing now is they're talking about the address range, which I will usually call the usable host. So basically what we have here is all zeros is the network number, all ones is the broadcast address. The first usable host will be one more than the network, so 172.16.0.1, and the last usable host will be one less than the broadcast address. So instead of 255.255 that we have for the broadcast, the last usable host would be 255.224. And of course all of these use our new / notation prefix for the subnet mask, which is /23. So that's taking a /16 and making 100 new subnets that are all the same size. Again, I think this would read better if this was a from. So what we're going to do is we're going to start with a /8 prefix, dividing on the first decimal point, the first octet, first byte, whatever you want to call it. And we want to create 1,000 subnets. So again, we need to solve the equation 2 to the n is less than or equal to 1,000 for the smallest value of n. and the smallest value of n that will do that is 10. So that gives us 1,024 networks. Of course, from the statement of the problem, we only need 1,000 of those. So we're going to borrow 10 bits. So by borrowing those 10 bits, our subnet mask goes from being on this first boundary between the first and second octet to being 2 bits into the third octet. The remaining of that third octet and the fourth octet become the host bits. So just like we did before, we are going to go through and basically count within the subnet bits. So the subnet bits, we'll back up. We started with a /8. We borrowed 10 bits. 8 plus 10 is 18. So this becomes a /18 network. So the first network is, we set all the subnet bits to 0, and then 1, then 2, then 3, then 4. So we just, again, count in binary from all the new subnet bits being 0 all the way up to the new subnet bits being all 1s. Right now we care about the network numbers for all these networks. So we're going to set all the host bits to 0, and then we're going to convert that to decimal dotted notation. So our first subnet, which would be referred to as subnet 0, because the 10 subnet bits equals 0, is 10.0.0.0/18. The next will be 10.0.64.0/18. And you saw a video in last lecture on something called the magic number, if you took my advice and watched that outside of the lecture. And so here the magic number is 64. That just basically means that the subnets are increasing by 64 between a subnet and the next subnet. Again, I don't like to use that to actually come up with the network addresses, but once you have the network addresses, you can notice, hey, there's 64 here, there's 64 here, there's 64 here, and kind of use it as a double check, if you would. Here, they're showing us the address range for the first subnet, subnet 0. So from above, we know that 10.0.0.0 is the network address. If we set all of our host bits to 1, that means 10.0.63.255 is our broadcast. One more than the network address is the first usable host. One less than the broadcast address is the last usable host in a subnet. So they're doing this for the 0 subnet. If you wanted to do it for some random one, like the 100th one, the process is exactly the same. So this video is talking about subnetting across multiple octets. In the example where we just borrowed 10 bits, that was a whole octet plus 2 more bits. So that's what we're referring to when we say subnetting across multiple octets. This video is about 5 minutes and 18 seconds, so I am going to play that here within the lecture video.
In classless subnetting, we've seen how we can borrow bits from the host portion of the subnet mask, and that the last one that's borrowed is the magic number, meaning that the last one, if we look at the place value of the 8-bit grouping, the last one in this case is in the 32's place, so the networks go up by 32. Starting with the 0 network, we have the 32 network, then the 64, 96, 128, so on and so forth, but the networks go up by 32. What about when we're subnetting from a Class A or Class B network address and subnetting generally in the other octets? Let's take a look at another example. This time we have a 10.0.0.0 network address and a classful Class A subnet mask, and we're going to subnet it. So we've taken the 8 bits and borrowed 3 bits, and now we have a /11 subnet mask. The last one in the subnet mask is still in the 32's place. If we look at this 8-bit grouping in this octet right here, the last one is still in the 32's place. So the networks will go up by 32. So the networks are the 10.0, 32, 64, 96, and they're going up by 32, but in the second octet. The only difference is now we have a lot more host addresses. We have 8, 16, 21 zeros for hosts, which means there's over 2 million hosts per subnet. For instance, if we take a look at this 10.192.0.0 subnet, the next subnet is 10.224. So that means that the host addresses go from 0.1 all the way up to 10.223.255.254 as the last usable host, and 255 is the broadcast. The next address is 10.224.0.0, which is the next subnet. All of these subnets are now /11. What about a more difficult scenario? In this scenario, we need to create over 300 equal-sized subnets of 20,000 hosts each, starting from the 10.0.0/8 network. So we need to create a lot more subnets, and we need a lot of hosts. Looking at this situation, we know that we're going to need to borrow bits from the host portion of our subnet mask. The question is, how many bits will we borrow? If we borrow 1 bit, we have 2 subnets. Now we have 4 subnets, 8 subnets, 16, 32, 64, 128, 256, 512. If we borrow 9 bits, we'll have 512 subnets that we create, and that will be sufficient to meet the demand for 300 equal-sized subnets. What about the requirement of 20,000 hosts each? We have 15 zeros left for hosts per subnet. 2 to the 15th power is 32,768 minus 2 would be 32,766 hosts per subnet. That meets the requirement of having at least 20,000 hosts in each subnet. So this scenario would work. You can see here that I've now highlighted the borrowed bits from the subnet mask. I've also converted it to decimal here, 255.255.128.0. And I've already ascertained that the last one in the subnet mask is in the 128's place, so the magic number is 128. The subnets will still go up by 128, but they'll also need to go up for every number possible in the second octet. If we look below here, we can see our subnets. The first subnet will be the 10.0.0.0/17 subnet, then the 0.128 subnet, then the 1.0 subnet, then the 1.128 subnet. And as you can see, we're iterating through every possible number in the second octet and then going up by 128 in the third octet. If I was to list out every possible subnet, we'd go all the way up to 10.255.0.0, and the next subnet would be 10.255.128.0. /17 is our last subnet, for a total of 512 subnets. In a situation like this, there's many more subnets and many more hosts per subnet, but the rule of the magic number still applies.
Okay, moving on to section 11.6.5, we have an activity which is calculating the subnet mask. So basically what they're doing is they're giving you the subnet mask. They're asking you to convert that to binary, and then once you do that, figure out the prefix notation. And once you do that, you can do a check and then a new problem. So you can go through and do those on your own. Next, that brings us to Lab 1166, which is doing some of the calculations that we saw in the last few sections of 11.6. I am going to assign this lab, so watch for it to appear in Blackboard. There are 6 problems, which I think might be a little too much repetition. So I usually do something like do the first 3, do the last 3, do the odds, do the evens. So you might want to look for a note that goes along with the assignment to see exactly which problems you're supposed to do. Also, you might get tied down. Most of the answers are in tables about IPv4 subnets. There is a reflection question, and I can't stress enough that the reflection questions are very important to answer and are often assigned more points than other parts because they are typically critical thinking type questions. So we'll move on to a section entitled Subnetting to Meet Requirements. But before they do that, we're going to talk about private versus public IP address space. We talked about public IPs being routable and routable over the internet, capital I. We talked about private IP addresses also being called non-routable because once you hit a router interface, those packets are not going to leave the local network. So a couple of things they're talking about is you have an intranet. That's typically defined as an internal part of a company's network. Although not necessarily a great fit, the other thing is an intranet could also be considered, for example, your home. Another term that I don't know that we talked about is DMZ, a demilitarized zone. What they're showing you down here is a real common circumstance where we have one router. Sometimes a DMZ would be made with 2 routers with the DMZ being between those 2 routers, but you can, if the router supports it, do a DMZ with 1 router. So what they're doing is you have an internal network, internal to your company in this example, and here we can use private address spaces because these machines will talk to each other. You will also have firewall rules that are pretty strict that protect your intranet. Then out here we have the internet, capital I. However, we're going to have some resources, for example, an informational website, maybe a website that has software, or a website that lets people on the internet purchase our products. So we have to relax some of the permissions in the demilitarized zone so that they can get to a web server or get to an application that allows them to do ordering, for example. So internet, capitalized public IPs, your DMZ is public IPs. However, your intranet is going to be private IP addresses. So they're going through some more subnetting examples where they're borrowing a set number of bits. And what happens is you're subnetting a /8. In this case, the first octet, the first 2 bits being 0, 1, makes it a Class A network. So the /8 would refer to the 10, which is the Class A private address space. So you're taking a huge subnet that has something like 16.4 million addresses, and we're going to just convert that to a /16. So in effect, we are borrowing 8 bits. And by doing that, they're going to go through and do exactly what we did before. Again, we can leave these in decimal dotted notation since this is an octet boundary. This is an octet boundary. So within the borrowed octet, we're going to count 0, 1, 2, 3, all the way up to 255. So if you did this in binary, that would be fine, but when you're subnetting on a octet boundary, a byte boundary, it is much easier to do. So here they have the network number, the broadcast address, and the range of usable host. The other thing we can do is if our subnets can do with 254 or less host addresses, we can go through and use a /24. So basically our subnets, we've borrowed these 18 bits here in the middle. So our /8 becomes a /24. And within these 2 bytes, we count 0, 1, 2, all the way up to 255. And then we go 1, 0, all the way to 255. And then 2.0. So we basically count with the 2 full bytes to go back and do that. I may have already mentioned this, but they're asking about the demilitarized zone. It needs public IP addresses because you want customers from the internet to be able to reach those services that you're providing in your DMZ. That's the whole purpose of DMZ, is to get them resources to what they need to do business with your company. This is called minimize unused host addresses and maximize subnets. So previously we were subnetting based upon the number of subnets we wanted. Now what we're going to do is do that based on the number of hosts per subnet, and only allow us to have enough host bits to cover what we need. That minimizes waste within the subnet and gives us a lot more subnets to use. So basically what we have here is we have a /24 network that we're given. And if we borrow 1 bit, it would be borrowing this first bit here. So we have 2 subnets with 126 usable hosts, all the way down to the /30, which would be 64 subnets with 2 usable hosts. So basically, maybe they don't completely show you in this section, but if we needed a whole bunch of subnets and the biggest subnet was going to have 10 hosts in it, then we would want to choose the /28. So that gives us 4 more addresses than we really need, but that's the closest we can get to 10 without going below 10. And then that gives us the maximum number of subnets that we can have. So they're calling that efficient IP subnetting. So basically, what we're doing is we've been given a /22. It's out of 172.16, which is the Class B private address space. And what we're doing is we are wanting 10 host bits so that we can have subnets as shown here that give us 1,022 host addresses. What we're going to do is we're going to look at our technology. I'm sorry, our topology. So here we have a corporate headquarters need 40, branch 1 needs 25, branch 2 needs 30, branch 3 needs 10, branch 4 needs 15. And then the other thing is we are going to need to assign subnets to each site and to the ISP. So we do have connectivity here that we need to deal with as well. So basically what's going to happen is we take the biggest subnet that we need, which is 40. We plug into the formula 2 to the n minus 2 needs to be greater than or equal to 40 for the smallest possible value of n that satisfies that. And here they show you 2 to the 6 minus 2 is 62. So that's the closest that we can get. So what we're going to do is we are going to change the slash 22 to a slash 26. So what they're doing here is we have the host portion of this. Okay, something's not matching up here. So they've made a mistake here. They said we had 10 host bits. They said we needed 6, so we should be borrowing 6. But what they've done is they've actually gone through and borrowed 4 bits. So they've changed it from slash 22 to slash 26. Like I said, they've made a mistake here. So what they're doing is they're going through and they're assigning all these subnets that have 62 hosts in them. So here we waste 22 addresses. Here we waste 32. So we still have some waste, but we're trying to minimize that. And then what they've done here is corporate to the ISP, they've given the 0 subnet. Here they've given the 064. Here they've given the 0128. So if you can go through, you can see that they've taken consecutive IP addresses and assigned them to either the different locations or the different point-to-point from a location router to an ISP connection. So apologize for that mistake they made. In this activity, you can go through and determine how many bits you need to borrow for different size subnets. And like you say, once you've done this, you can do a check and it will check and see if you've done your work correctly. 1175 is a subnetting packet tracer where you go through, calculate some subnets, assign them to devices in the topology, and then check and make sure you did that correctly. So that's packet tracer 1175. I'm pretty confident I'll be assigning that, so watch for that to appear. So the next thing is VLSM. Usually, I talk about it and then they show a video. In this case, they're showing the video first, but I'll give you a little lead in. In the last portion of section 11.7, we talked about minimizing waste. But when you have different size subnets or different number of end user devices in a subnet, you still, as you get to smaller and smaller networks, have more and more waste. So you're not wasting hundreds or thousands or millions of IP addresses like you might be in other scenarios, but there's a way that we can get less waste than what we've talked about before. So this first video is 2 minutes and 31 seconds and is basically talking about the basics of variable length subnet mask.
The basics of VLSM, or variable length subnet masks, works like this. 1. Subnets do not have to be equal sizes. as long as their address ranges do not overlap. So we can create unequal sized subnets. They do not all have to be the same size. 2, when creating subnets, it is easier to work from larger to smaller subnets. So for example, I have the 192.168.1.0/24 network. I subnet the network into 4 subnets /26 subnet masks. So the subnets go up by 64. I now have 4 equal-sized subnets. With VLSM, or variable length subnet masks, I can decide that I want to change one of these subnets and further subdivide them into smaller subnets, as long as the address spaces that I create, or the subnets that I create, do not intrude into the other subnets. For instance, I could take this 192.168.1.192 subnet. The address range for this subnet goes from 192 all the way up to 255. What I can do is I can say, instead of having this subnet /26, what if I take that address space and divide it into 2 smaller subnets size /27 each? If I do this, I effectively have created 5 subnets. The 3 subnets up here are 64 hosts each, and the 2 new subnets that I created from the 4th subnet are 32 hosts each. The reason I can do this is because my 2 smaller subnets do not intrude into the larger subnets. This is variable length subnet masks. In this situation, it has also allowed me to create 5 subnets, thus escaping the equal-sized subnet limitation of creating subnets in powers of 2. This gives me greater flexibility and allows me to create subnets of different sizes based on the requirements of my network.
Okay, the one comment I want to make is when they did the subnetting, they did some /26s, and then they took the last 2 and made them /27s, which will work fine if that matches the topology. But a lot of times you'll run in situations where you start with a couple of /27s, then you might have some /28s, and then you might have some /29s, and then some /30s. So it's not always the very last subnet that you're dealing with or making the changes. So 11.8.2 actually gives you a detailed VLSM example. It's about 10 minutes, 23 seconds long, but I think it is important to play that here within the lecture video.
Networks for 2 hosts each. Before I begin to create these subnets, I need to check to see if I even have enough addresses in this address space to create all of these subnets. So by writing out the network and the subnet mask in binary, we see that we have a /23 subnet mask. Here's 23 ones in binary. The last bit is in the 2's place. If we look at this 8-bit grouping in the 3rd octet, we see that the last one is in the 2's place. That means the subnets would go up by 2. So the next subnet will be 172.16.2.0/23. So the address space that we're working with goes from 172.16.0.0 all the way up to 1.255. Let's see if this is enough addresses to create all of these subnets for this specified amount of hosts. I can see that starting from a /23 subnet mask, we have 9 host bits, so effectively there's 512 hosts. If we look at each one of these subnets that we're going to need to create, I cannot create a 200 host subnet, but I can create a subnet for 256 hosts. That number does not reflect the usable hosts, but the total number of addresses in the subnet. Similarly, I'm unable to create exactly a 100 host subnet, but I can create a 128 host subnet, a 64 subnet, a 32 subnet, a 16 subnet, and four host subnets will satisfy these requirements. If I add up all of these numbers, 256, 128, 64, 32, 16, and 4 subnets of 4, the total number is 512. So I'll have exactly enough host addresses to create these sized subnets and meet the requirements. Once again, these numbers here for the subnet sizes that we'll create do not reflect the usable host addresses, but the total number of addresses in the host portion of the subnet ranges, including the network address and the broadcast address. So let's get started subnetting this network using VLSM, variable length subnet masks, and working from largest subnets to smallest subnets in order to create all of the subnets required. So working from largest to smallest, the first thing I need to do is to create a network for 256 hosts to satisfy the 200 host requirement. What I can do is I can subdivide this single network of 512 hosts into two smaller subnets of 256 hosts each. So instead of having a 172.16.0.0 network /23, I change the subnet mask to /24. This creates two networks, 0.0 and 1.0, each subnet having 256 or 8 host bits. Notice how the subnet mask has changed from /23 to /24, and I now have two 256 host subnets. What I can now do is keep the first of these subnets and subdivide the second one. To do this, I simply take this 172.16.1.0/24 subnet and change it from /24 to /25. So now I have the 172.16.1.0/25 subnet. This creates another subnet, 172.16.1.128. Both subnets have a magic number of 128, meaning the networks go up by 128. So I've taken this one network of 256 hosts and subdivided it into two networks of 128 hosts each. Now I have a subnet to meet this second requirement. Moving on from there, I'll keep the first of these subnets and then further subdivide the second one. So now we no longer have the 1.0 network in its place. We have the 1.0 subnet and the 1.128 subnet. Then I subdivide the 128 subnet into two smaller subnets /26 each. So now there's no longer a 128 subnet, there's two subnets in its place, a 128 subnet and a 192 subnet. Both of these subnets have a /26 subnet mask. If I was to write this subnet mask in the binary conversion table here, we would see that in the fourth octet, /26 means that the last one in the subnet mask is in the 64's place, and the networks go up by 64. Furthermore, with the /26 subnet mask, you only have 1, 2, 3, 4, 5, 6 host bits, and 2 to the 6th power is 64, meaning there's 64 hosts, 62 usable per subnet. I now have my 256 host subnet, I have my 128 host subnet, and my 64 host subnet. I can subdivide the second of these two subnets into two smaller subnets of 32 hosts each. To do this, I take the 192 subnet and subdivide it by changing the subnet mask from /26 to /27, creating two subnets of 32 hosts each. So now I'm no longer using the 192 subnet /26, I'm using it as a 192/27 subnet and a 224/27 subnet. From here, I still need a subnet for 10 hosts. I can take the second of these two subnets for 32 hosts and subdivide them to two 16-host subnets. To do this, we take the 224/27 subnet, change the subnet mask from /27 to /28, and now I have two smaller subnets. From here, I take the second of these two 16-host subnets. I only need one. The second one I'll use for 4 subnets of 4 hosts each. So now instead of the 240/28 subnet, I have the 240/30, the 244/30, the 248/30, and the 252/30 subnets. Looking at the subnets that have been left, we have the 172.16.0.0/24 subnet. This is good for 256 hosts. We have the 172.16.1.0/25 subnet. This is good for 128 hosts. The 172.16.1.128 subnet /26 is good for 64 hosts. And the 192/27 subnet is good for 32 hosts. The 224/28 is a 16-host subnet. And then the last 4 subnets /30 each, 240, 244, 248, and 252, are good for 4 hosts each. Once again, these sizes do not reflect the usable hosts in each subnet, but the total number of addresses in the host portion. For usable host addresses, you need to -2 from each subnet. If we examine the host addresses closely, we'll see that none of the subnets overlap. In other words, this 172.16.0 subnet goes from 0 all the way up, since it's /24, to 255. You can see that the next subnet starts at 172.16.1.0, so the two subnets do not overlap. Similarly, this second subnet goes from 0 to 127, and we can see that from host 0 to 127, the next subnet at 172.16.1.128/26, that there's no overlap. This subnet ends at 127, the next subnet begins at 128, and so on and so forth. In the end, we've created 9 subnets of different sizes: a 256, a 128, a 64, a 32, a 16, and 4 4-host subnets. This is VLSM, and it allows us to create subnets or networks specific to the needs of the network.
Okay, I think that was a very good example of variable length subnet mask. The one thing that I am not exactly sure they mentioned is what they gave you as a starting point was an ordered list. That is, it was in the order of the largest number of hosts needed down to the smallest number of hosts needed. A lot of times you're just given a topology diagram, and the first thing you have to do is order it from largest number of hosts to smallest number of hosts, then start through the variable length subnetting as they showed. So 11.8.3 is going to take kind of a step back and talk about basic subnetting scheme again, which is the first thing we looked at, where we end up with fixed size subnets for however many networks we need. So here we have 1, 2, 3, 4, 5, 6, 7 subnets that are needed. Now, probably on homeworks, I'll give you a diagram like this and say, okay, how many subnets do we need? A lot of times what students forget is, even though this is a point-to-point connection between two routers, this has to be its own subnet. And we need 2 IP addresses to do that. So with this basic scheme, we're going to solve this for 2 to the n is greater than or equal to the number of subnets that we needed. So we're solving for 2 to the n is greater than or equal to 8. Well, 2 to the third is exactly 8, so that is the smallest value of n that will satisfy that. So what happens is they divide this into a subnet and a host portion for that subnet. And we create these. So we have the 8 subnets we talked about. Again, the number of usable hosts is 2 to the n minus 2, where n's the number of host bits. So in this case, we have 5 host bits. 2 to the 5th is 32, minus the 2 makes 30 usable hosts per network. So basically, they've gone through and they've assigned the different networks from this network table to each of the 8 networks that are needed, or the 8 subnets. So each of these have 30. So here we're wasting 5 host address, not too bad. Here we're wasting 10. Here we're wasting 15. Here, this is the best one, we're only wasting 2 addresses. But down here, the wide area network connections, each one of those we're wasting 28 IPs, which is quite a bit of waste. So this is showing us just what I said, how many is wasted. So again, you should already know from the 2 videos in the chapter that if we want to reduce that waste, then we're going to use variable length subnet mask. So basically, what we're doing is, here's the traditional 8 networks that each have 30 hosts. What we're going to do is we're going to divvy these up so that we have 2 hosts each on the WAN links. So we're going to save some IP addresses by eliminating that waste. So basically, here we have the same topology, the same requirements as before. So what we do is, this was the fixed length. What they're going to do is they're going to go through, and we actually could do, we have 30 usable hosts. The next breakpoint would be 14 usable hosts. So, we're not going to be able to start doing the variable length subnetting mask right away. So what they're going to do is they're going to take this last subnet and they're just going to carve out some 2 host WAN addresses for that by using variable length subnetting mask. So what happens is we're going to go through and subnet that further by borrowing 3 more bits. The reason we borrow 3 is we want to get down to 2 host bits so that we have 2 usable hosts. And then we're going to take the first 3 and assign them to these WAN connections, router to router, router 2, router 3, router 3, router 4 networks. And then that gives us some more address space that we could use. Again, if we added more routers, it would give us some WAN addresses, for example. So here they're just showing us those IP addresses being assigned, the new /30s down here being assigned in the topology. So what they talk about is, they say without unnecessary waste. We can do even better if the size of the networks kind of varies, so that we can kind of subnet down like they showed you in the second video. So I will give you some examples outside of the formal curriculum related to this. So what happens is, here we have I guess the same topology as before. So they're just going through showing us with variable length subnetting mask. what the IP addresses would be. I'm sorry, the network addresses would be, what the address range will be, and here they're actually talking about the default gateway, which would be, looks like they're using the first usable IP address in the network to be the default gateway for these 4 local area networks up there. So they're just going a little further as far as the IP ranges and what the default gateway would be. 11.8.6 is an activity to practice the subnetting, or at least using variable length subnet mask. You can do that on your own and then check yourself. They have a second table down here. Instead of doing a new problem or something, it looks like they're giving you 2 tables, and you can check that. So you can do those on your own. And then we'll move to structured design. And what they mean by structured design is basically making sure you plan your network out correctly. So, a lot of this you can read on your own, but they're basically going through saying, okay, determine if you're going to use public or private IP addresses. Once you do each of those, again, using public for the DMZ, private for your home network or your intranet if you're talking about a company. If they give you a /8, or if you use a /8 for a private network, that's going to give you 16 million hosts. So you're not going to have a problem, most likely, fitting your network into 16 million hosts. In a home router, sometimes they use a 10 subnet. Say, fine, you can have up to 16 million hosts in your house. But a lot of times they'll use like 192.168.0.0 or maybe .1.0, and they basically allow you to have 254 IP addresses within your home network, which even still these days we're getting more and more devices, especially with Internet of Things, that might have IP addresses, but usually for a home 254 addresses would be fine. So then you can go through and plan out your network or your subnets. You need to go through and assign them to devices. Several things that you need to think about when you're planning your network is how many end user clients you're going to have. Your cell phone, your laptops, your desktops, your printers, most modern TVs, sometimes your refrigerator, your DVRs, your tablets. There's a lot of things that are going to need IP addresses. Typically, end user devices get their IPs out of a range provided over DHCP, which again is Dynamic Host Configuration Protocol. We haven't talked about them yet, but we'll talk about in the next chapter. If we're talking about IP version 6 addresses, there is a version 6 of DHCP, but there's also something called SL AAC, from which an end user device can take information from the router and determine an IP address that it might be able to use. The other thing, though, is servers. If you have a file server in your house, or you have a DVR that you might need to connect to, you would like it to always have the same address. Printers are the other thing. So if you have a wireless printer, you don't want to have to be reconfiguring the printer every time you power cycle the router and it gets a new IP address. So some things need to be accessible with an IP address. Usually doesn't happen in your home, but in a place of employment. you might need to get to host from the internet, capital I. There's a couple of ways we can do that. We can do that with network address translation, or we can require a person to connect and authenticate to our VPN, which will give them an IP address inside our company. Intermediary devices, these are your routers, your managed switches, your firewalls, things like that. They have to have IP addresses so you can connect to them and manage them. You want them, just like the DVR example I gave or the printer example, you want them to have predictable or known static IP addresses that do not change. And then for each of your networks, you need to have a default gateway. Again, oftentimes the default gateway is the first usable IP address within a network range. That doesn't have to be the case. I've seen it be the highest usable before. It can actually be a random one. It needs to be fixed so that all the hosts can communicate with it. But you could say, I want my default gateway to be .33, right in the middle of address space. But a lot of people use .1 just because it's easy to remember and easy to tell people. Packet Tracer 1193 is a VLSM design and implementation. So it's similar to the previous packet tracer. However, instead of using basic subnetting, you're using variable length subnet mask subnetting. So I will be assigning that, so watch for that to appear in Blackboard. And we'll move on to the practice and quiz section. First thing it does is it starts with another packet tracer. It is on variable length subnet mask again. I probably will be assigning that, so watch for that to appear in Blackboard. Down here we have a lab, which is basically the same as 11.10.1 packet tracer. However, if you were in class doing this on real equipment, you might do the lab instead of the packet tracer. So I probably will not be assigning this, but you should probably still at least glance over it to see what the purpose is of the lab. Okay, we're up to the what did I learn in this module. You can go through and read the summary of the things we learned about. It's actually relatively long for Chapter 11, way longer than typical, but these are all the things that we talked about. And that brings us to 11.10.4, which is the module quiz. And as always, you can do that on your own to make sure you understand the information from this chapter, this module.